That out of the way, we have Pavel giving his last talk of this mini course series.
Thank you. So yeah, I will be actually a completely new topic, unrelated to what I was talking about for the previous 3 talks. There will be no perturbative path integrals here, but there will be some kind of completely different line of thinking about combinatorial topological field theory, or rather combinatorial topological conformal field theory. So I will explain what I mean. So this topic a little bit more on the experimental side. So well, there's the word towards here. So it's a project in progress. And well, it's joined with Justin Beck, who is in the audience, and with Andrei Losov. Well, kind of here is a kind of a snapshot of our thinking at a particular moment of time. And a big chunk of today's talk will be various pieces of motivation, kind of what we would like to have, and also what we actually do have. So as a piece of warm-up, the following rather well-known model of 2-dimensional topological field theory. So well, it's known as 2-dimensional Dijkgraaf-Witten model. So you fix a finite dimensional associative algebra. So let me call the product M2. So by now, maybe you know why I want to put 2 here, because it's a binary product with 2 inputs, and also with an invariant in the product G. So associative algebra with a pairing G. So with a pair. So I can use the pairing to sort of construct an operation. So M2 is an operation which takes 2 inputs in V and spits out an output in V. Then I can use the pairing to construct an operation which eats 3 inputs in V and constructs an output in the ground field. So let me call it K. It could be real, so it could be something else. So let me call this operation C3. So it has 3 inputs and kind of output in the field. So C3 is invariant under cyclic permutations of inputs, and that's sort of the condition of compatibility between the pairing and the product. So then, if I take some surface, 2-dimensional surface, and well, let's say I triangulate it somehow. So let's use T at triangulation. Then, well, what I want to do is the following. I want to construct a number given this algebra. So what I want to do is I want to put inside each triangle the structure tensor C3. So I can think of C3 as a sort of as an element of V dual U. So I put a copy of C3 in each triangle, and then I contract well where the edges are. So maybe another visualization of what's going on is to draw kind of a dual ribbon graph here, and then I'll be sort of putting my structure tensor at each vertex of the ribbon graph and can contract the structure tensors along the edges of the ribbon graph. So the result will be a number. So let me call this number the transition function. So it's well, schematically, so I take the tensor product of the structure tensors over all well, 2 simplices. And well, I contract it with the tensor product of the, so I'm contracting using the inverse metric. So maybe I forgot to say inverse. So each edge should be created with the inverse metric. So this is a number in the ground field. So then one might ask, so okay, the desire would be to say that the triangulation doesn't matter. So that if I change the triangulation, then this number stays the same. Well, how could one check this? Well, there is Mnev's theorem that tells you that if you have 2 different triangulations of, well, let's say 2-dimensional version of two triangulations of a surface, then I can sort of go from one triangulation to the other by a finite sequence of local reconstructions, local moves of a triangulation, and there are two types or three, depending on how you count, of these moves, and they are called Buckner's moves. So there is one move which is called the flip. So if you have two triangles which share an edge, then I can just flip the diagonal in this relational. So that's one type of move, and sort of there's a triangulation going on outside, and you just don't touch it, so it's a local move. So that's, let me call it Buckner 1 or Buckner flip. And the other move is that I can take a triangle and sort of put a new vertex inside it and subdivide it into three triangles. Or I can reverse it. So I can move from this picture back. So, let me call it the second Buckner move, or stellar subdivision, stellar aggregation, depending on the direction of that move. So to check that this number is invariant under the choice of triangulation so it would suffice to check the invariance under Buckner's moves. And well, actually for the Buckner flip, it actually follows from associativity of M2. So the invariance follows from associativity. So essentially what happens here is if I put, I don't know, X, Y, Z, it's three of the edges here. So I'm asking whether X times Y times Z in brackets is the same as X times Y in brackets times Z. And that's the same, that's associativity property of M2. So it works by associativity, so it has invariance. So for the second Buckner move, it doesn't work automatically actually, but it works if for a certain class of such structures. In particular, if I ask that my pairing is something very particular, it is well essentially, well, one could call it a giving form. So if it's constructed from the product in this way, so as this sort of trace of this operator, then you will have invariance under this. So yeah, these structures you could also call them non-abelian Frobenius algebras if you like, because sort of pairing is important in this game. But I'm not requiring that M2 is commutative. I'm not requiring that. Okay, so
the condition that guaranteed the second pattern.
so what's the question?
So what was the thing about G that implied the pattern move is set aside?
Yeah, so this is the condition that G is given, it can be recovered from by this formula. It's almost if and only. So under some mild extra condition that sort of the range of M2 is the entire V, that would be if and only. Okay, so now this here I was kind of thinking about a surface, a closed surface with the triangulations, and then, well, let me assume that G does satisfy this property. Then indeed I have some kind of numbers that don't depend on the triangulation, but will depend on the topology of the surface. I can also include boundaries in the game. I can consider surfaces with boundary and sort of then triangulate the surface with boundary. Then, well, the story extends, and I will write essentially the same formula. But if I have a triangulation of a surface with boundary, then somehow not all copies of B star that occur here will be contracted using the edges, because sort of there will be sort of the outer edges. So the result will not be a number, rather it will be a map between two vector spaces. So then you can interpret the partition function of a triangulated quadrism, so that it will be sort of a linear map from some space of in states to the space of out states, where kind of the space of in states, it's so for instance, if there's one incoming circle, it would be V to the tensor power the number of intervals here. Or if you have several circles, then incoming circles, then appropriate tensor power of the space of states for a single surface. For a single circle, for instance, it would be e to the tensor power the number of intervals into which my triangulation subdivides that circle. And well, and if there are several circles, then it's product of such mechanisms. And likewise for the outer boundaries, you also have the outer space of states. So what you will obtain is a partition function as a linear map from the in space of states to the out space of states. So the whole thing arranges into sort of IKEA style TQFT. So as a functor from two cobordisms, two vector spaces, but okay, two cobordisms equipped with triangulation. So well, I want to say that somehow things are independent of triangulation, and for a closed surface, yes, they are independent, as I just said. For a surface with boundary, well, there's kind of some extra wrinkle because, well, we have sort of different sizes of the spaces of states which depend on the triangulation of a surface. But it turns out that there is kind of some natural reduction where you would assign some kind of a smaller space of states to a circle which doesn't depend on a triangulation. So this reduction is essentially that if I look at some triangulated cylinder with, then well, it will give me an operator out of this space of states v to the tensor power k, and this operator will have a kernel. So if I quotient out that kernel, I will obtain a reduced space of states. And this reduced space of states for a circle is independent of triangulation, and it can be identified with the center of V, or if you like, with V most commutant, or with zeroth Hofstad's homology, if you like, of V with coefficients in V.
Sorry, I didn't quite understand. So when you have the cylinder, on the one side, you have the thing with k points, on the other side.
With some other number of points, it turns out that you can consider any triangulation here and look at the corresponding map. Then if you take the quotient by the kernel, it will be independent on L, on K, and on the triangulation. So there will be a kind of functorial isomorphisms between such quotients for different choices of K.
So even if you have L equal to K and have a triangulation which is simple, you still get a kernel of the map.
Absolutely. Absolutely. There will always be a kernel, yes.
You're saying independent of what triangulation of the cylinder on the other side shows that kernel is the same.
No, the quotient by the kernel is the same. So I can increase the number of K's here. Yes, then the kernel will increase and the quotient will stay the same. Okay. Yes. Okay. So that is somehow a way to say that this sort of functor out of the triangulated cobordisms kind of factors through a functor from non-triangulated cobordism, just the usual one. So there's kind of a reduced TQFT here, which doesn't depend on triangulations. So, and this is kind of an honest ITS TQFT. So, right. So, and there is a particular, okay. So it depends. So it assigns numbers to closed surfaces and linear maps between sort of spaces of states. And here I wrote the space of states for a single circle for surfaces with boundary. And a particularly famous example here, and that's closer to the original diagram with the paper, if I take my algebra to be the group algebra, well, let's say with complex coefficients of some finite group G. So pick a finite group, look at its group algebra. So then it has this structure, so a product and the magic or blending. So then yes, so one can calculate explicitly what this functor is. Let me tell you what are the numbers that this kind of what is the partition function of a closed surface? So it will be just some number. So if it has genus H, then this number is, so it's kind of a famous formula. So it's the sum over irreducible representations of the group. And well, what you're summing is the dimension of the representation divided by the size of the group raised to the power the Euler characteristic of the surface. It's kind of a famous formula, and it has a nice topological meaning. It's a rational number, but it's not a kind of an arbitrary number. It has a nice meaning as the groupoid volume of the groupoid of G coverings of the surface. So you're kind of counting coverings with kind of weighing each one with 1 over the size of the isotropic unit. Okay, so now that was kind of one piece of motivation, and where we are kind of going now with this, where we want to go, is that we want to relax the invariance with respect to partner nodes. So we now want to relax the invariance to invariance somehow up to homotopy. So now I want to move in the direction where there will also be triangulations, but the effect of a partner flip will be kind of Q exact for certain differential Q. So Q will be a differential on V, and also on the on various tens of powers of. Let me sort of schematically draw this generator here as a sort of square without a diagonal. And likewise, I want to relax the invariance with respect to the second partner move, also up to homotopy. And there will be also some kind of generator here. And kind of let me schematically denote this generator as a triangle with a dot. So that's just pictures. So what's kind of the vague physics intuition here? So I want to think of triangulations as some sort of combinatorial analog of a metric on the surface. Yeah, please.
I think this is a very dumb question. I've missed now what Q is. What is Q here?
Okay, so Q will be some kind of differential, and it will be a differential on V. And
okay.
it will also be a differential on powers of V. No, it's not a dumb question. So in particular, so here it would be acting on kind of the space of states for the boundary of this picture, which is V to the tensor power 4. So yes, so physics intuition is that well, triangulation is a model for a metric on the surface. So then, well, so here I'm kind of locally changing. Triangulation is like locally changing a triangulation. So and the effect of locally changing a triangulation in the field theory is called stress energy tensor. Or so yeah, stress energy tensor exactly measures that. So the right hand side, I want to call it the stress energy tensor. And here I'm saying that the stress energy tensor is somehow Q exact. So okay. Now kind of the next bit of motivation. So that's not a very standard terminology, but following Andrei Losov, I want to call this setup H TQFT. So H is I think it's supposed to stand for higher, so higher topological quantum field theory setup. Maybe we would object to this terminology. Another name for it would be something like Cochin level cohomological field theory. But let's go with it. So okay, so here's the idea. So in kind of Siegel's picture of combinatorial quantum field theory or geometric combinatorial quantum field theory, you have partition functions for manifolds with boundary. Let me draw some schematic manifold with boundary here. So this, okay, so where does it live? So it's a map from the in space of states to the out space of states, but it also can depend on the geometry. And which type of geometry depends on the particular field theory. For instance, metric or maybe conformal structure. So it's a function of possible geometry. So if you choose a geometry, then you have a linear map. So geom stands for possible geometries, admissible geometries in the model. What happens in higher topological quantum field theory is that, well, very similar. So Z of a surface would be, okay, it would be also a homomorphism from the in space of states to the out space of states. So one kind of wrinkle is that now everything will be kind of spaces of states will be chain complexes. So they will carry a differential, which I will call Q. And also, instead of functions, I should put here differential forms of geometries. And here there are really differential forms of different degrees. So the projection function will be a non-homogeneous differential form, have components in degree 0, 1, 2, 3, and so on. And sort of the topologicity kind of property here is an equation. It's an equation that the differential along geom plus q, and well, I'm not thinking about signs at all here, plus q annihilates z. So this is kind of a topologicity property in this sort of Lex version of topological quantum field. So it's useful to look at the what this equation means for the lowest de Rham degrees. So for instance, so C in particular has components in de Rham degree 0, 1, 2, and so on. So the zeroth kind of component of this equation tells me that Q of Z vanishes. So Z0 is Q closed. So for a geometry, it's a function of geometries. For a fixed geometry, it gives me a Q closed map from between the spaces of states, or if you like, that's the same as to say it's a chain map between its spaces of states.
Sorry, what did you say is the Z upper 0?
That's the zero form component.
Okay.
Right? So it has like various form components along geo. So, and if I look at the next equation that's hidden, so this kind of a hierarchy of equations. The next equation in the hierarchy tells me that if I take Z0 and take its differential along geom, it will be, well, Q of something, Q of Z1. So that tells me that if I change the geometry a little bit, then my chain map between spaces of states changes by well, a Q exact map with sort of Z1 being the chain homotopy.
Question.
Yeah, please.
I'm not sure I really understand what the space geom is supposed to be.
Right. So so far I'm keeping it completely abstract. So I will have an example in a moment. But so for instance, in sort of physical field theory, you can imagine that that's I don't know, everything depends on actual Riemannian geometry or pseudo-Riemannian structure, let's say, on the manifold. Or it could be something different. For instance, it could be a conformal structure or a complex structure, or I don't know, a flat bundle. It's some kind of local geometric data.
In each of these cases, the differential B is
It's a differential. It's a de Rham differential acting on forms on the space geom. So how I should interpret this? So this is kind of a function of geom, and this is sort of infinitesimal change of Z0 as I change a little bit geometric data.
And the H's are now chain complexes, and the Q is sort of the chain
Yeah, exactly.
differential in those things.
Yeah.
And use differential for the harms, right?
Exactly. So by abuse of notation, Q is all differentials in the game. So yeah, but starting from those, yes. So differential on each H, and also the induced different. Yeah, exactly what you said. Exactly what you said. So there are various examples. Yes, please.
So this is like the round cycle straight wave.
So far there are no triangulations. So you're looking there.
No, I'm looking at this.
Here there are no triangulations.
Not a check. It is a double complex, but it's just the degree on the Hom complex. Not a check Durham. It's just a Durham.
No, but we have like a sequence of forms, the differential of like.
Yeah, there's a Durham direction. That's the geom, and then Q is just the internal gradient.
Okay.
Yes, exactly. Yes, things on. That's right. So yes, so there are various examples of this structure, and well, given time, I would have given you more examples, but let me focus on two-dimensional examples. There's actually a very cute one-dimensional example, which is called M equals 2 supersymmetric quantum mechanics. But let me go directly to the two-dimensional example. So, and well, without any details, but sort of two-dimensional conformal field theories I left a space before C here, for conformal. So two-dimensional conformal field theories with the property that stress energy density is Q of blah. So this blah, so Q is the BRST operator, so it's a differential on the space of local fields at a puncture, or equivalently on the space of states at a tiny circle. So you can think of puncture as a tiny disk out of a surface. So yeah, so Q is called usually BRST operator, and this blah has, for some reason, there's a standard letter for it. It's G. I don't know why it's called G, but it's a standard notation. So then one can consider correlators in this conformal field theory. So you can take a surface with a bunch of punctures. Let's say puncture at 0, 1, 0, 2, and so on. Sorry, Z1, Z2, and so on, Zn. It could be a surface with some genus. So, and then I can put some kind of local fields here, P1, Pn, and then one can consider the correlator of these fields at those plugged in those punctures. And it turns out to be useful to also have a separate set of punctures, maybe P of those, P of green punctures. And in the green punctures, you would put this field G, this kind of super partner, if you like, of the stress energy tensor. So you put several copies of the field G. So it turns out that one can interpret this correlator as defining a P form on the moduli space of complex structures on the surface. Like you put the twiddle here, and I'll say what the twiddle means. Okay, yes. So it can be interpreted as a P form on the moduli space of complex structures. So twiddle means, so N, it means N punctures. P is the number of G insertions. H is the genus. Twiddle means that I want to remember formal local coordinate near each puncture, and that has to do with the fact that sometimes you want correlators of not just primary fields but also descendant fields. So kind of to be correct, you need to remember this formal local chart. So yeah, and if you want to really understand how such correlators give you a P form, then well, you should understand that well, a P form on the moduli space should be evaluated on a P tuple of tangent vectors to the moduli space. Tangent vectors are given by the Beltrami differentials, so you should actually contract each field G with the Beltrami differential. So actually, those kind of green points are traveling on the surface and are being contracted with Beltrami differentials.
Sorry, could you say again what the tilde meant?
Tilde means that we want to remember a local, well, a formal coordinates near each puncture. Okay, thank you. So I don't know a proper name for this moduli space. It's appeared for sure, for instance, in the famous paper of Zwiebach.
Oh, sorry, what are the subscripts on the N?
H and N. So H is the genus, N is the number of punctures. So, and it turns out, and this is kind of, okay, so first of all, if I allow phi's to be allowed to myself to vary phi's, then I would say that the result is a form on the moduli space with coefficients in the home from, well, the space of local fields that I can plug in the puncture, which is the same as the space of states for a tiny circle, homes from the nth power of that to complex numbers. If I think of the punctures as kind of incoming tiny circles. That's kind of allowing myself to vary phi's. So it's an object very much like what I was talking about here. So it's a differential form in certain space. Instead of geom here, I have this M twiddle. And moreover, and it is something kind of that can be proven by standard technology of conformal field theory. By the way, when I write this formula, then I should put the letter T here. So that's exactly what a TQFT is. It's a conformal field theory with this property. So yeah, so what you have is that the differential along the moduli space plus Q annihilates all these objects. So let me call this collection of correlators understood as P forms. Let me call it Z, and this is kind of the P form component of Z. So then I have that I have my kind of main equation. For instance, like examples of this equation, if fees are Q closed fields, then this is actually the round closed differential form on the modular space. Okay, so this is kind of a brief remark about two-dimensional TCFTs.
Can you maybe repeat again what exactly Z is in this case? So I guess what you wrote up there is Z, so the P component of Z, right?
Yes. Z is just a non-homogeneous form whose component in degree P is this. I can, if you like, I can write C bullet or something. So Z is a non-homogeneous differential form. Here I explained how to construct its Pth.
And the fields phi and the punctures is data that I fixed beforehand or that goes into.
So when I write it this way, then I mean that well, punctures can travel around and somehow their position is recorded by the point in the moduli space. When I write it this way, that means that I can choose arbitrarily my fees, and when I have chosen them, I plug them as inputs here in this homes, and then I obtain an actual differential form on the moduli space. Yes, please.
So is that ZP the correlator above?
Exactly.
Okay.
Yes, CP is the correlator above with P insertions of the G field.
Does G have? Can you say more words like how G is described in different contexts? I guess maybe asking particularly from their life. What is G?
I don't know why it's called G, but sort of this is kind of its defining property. So yeah, so somehow stress energy tensor is not zero. So the theory somehow reacts to well changes of, well, let's say conformal structure, but it reacts somehow in a Q exact way. So G is a homotype. So the mathematical way for G would be a homotype.
So why there's no coordinates for G?
Yes. So okay, there should be coordinates x1 dot xp. But then that's what I was trying to say in words, that how to understand this as a P form on the moduli space. So if I should be able to substitute a P tuple of tangent vectors, and then tangent vectors to the moduli space they're described as Beltrami differential. So I should integrate over the surface with the Beltrami differential everywhere. So somehow points X are kind of integrated with against the Beltrami differential. But yeah, so good questions. I'm sorry. Yeah, please do interrupt me with yes. So to make things clear. So now another model for two-dimensional TCFT, specifically in genus 0, and here, well, in genus 0 is it's called the algebra over the framed little disk operand. And this I think appeared in Owen's talk yesterday. So so another description for a two-dimensional TCFT in genus 0 as an algebra over the framed operand of little disks. So here somehow I'm thinking of my, first of all, I'm in genus 0, so I should be thinking about a sphere, for instance, but then I want also to blow up the structures into actually finite round holes. So in the end, I want to consider configurations, probordisms of special type that are kind of standard unit disk on the plane with several smaller disks cut out. So and I also want to mark a point on the boundary of each disk. So on the outer circle, it's a standard point, kind of 1, and on the inner disks, they are arbitrary points. So then such configurations of disks are called E2 framed operands. They are framed operand of little disks. So the operand structure is kind of the composition gluing of surfaces, if you like, or composition of such pictures. How the composition goes, I just take one such picture, scale and rotate, and plug inside one of the holes. So that's how the operatic composition works. So then a 2D TCFT and genus 0 in this language is it's an algebra over this operand. So that is to say that it is a kind of chain complex of kind of states for a circle, together with a collection of differential forms on this configuration spaces of disks. So you have kind of or like fixed n the number of small disks here, and well, you will have also the form degree. So this will be a P form on the configurations of n disks with coefficients in ohms from, well, here I have n kind of incoming circles and one outgoing circle in this picture. So an algebra over such an operand is exactly a collection of such differential forms satisfying the equation that we would like to see here, satisfying the equation that D on the configurations of disks plus Q annihilates C. So for every fixed n, and this equation sort of mixes the different theorem components.
Sorry, I didn't understand what this statement is. Are you saying if you have a module, an algebra over the framed E2 disk operand, then you automatically get this data?
Yes, the algebra is algebra over the E2 framed operand is exactly such a collection of differential forms. And yeah, this is this is a kind of PG. Well, yeah, this is just a part of the definition of the operand, of the algebra over an operand.
Don't you also need to talk about composition of modules?
Absolutely. Also should be absolutely should be also compatible with respect to compositions.
And does that correspond to a specific? I mean, there's a whole host of different models for this framed operand. You're saying it's a specific model for the framed operand such that this is true.
So I'm saying that well, I fixed my model for the operand, but there are lots of different algebras over the operand. I'm saying that such algebras, well, an algebra over an operand is a collection of differential forms with this property.
This is a model.
Sorry, maybe not everybody knows what the non-operand is.
Right. So well, you don't have to know what an operand is. It's the structure of gluing surfaces in this case, of concatenating surfaces. So along boundaries. So here it means that I can take. I think of it as a surface with some in boundaries and one out boundary. And I can take another surface with a single out circle, and they can sort of glue it inside this one.
Yeah, but you're doing differential forms on something, right? So what's
Yes.
that something?
Yes, this something is the configuration space of configurations of n little disks inside the big disk. So for each disk, I should remember its position, its radius, and this point on the boundary. And the disk should be non-overlapping. So that's it. It's a finite dimensional theoretical space.
Do you fix Q or do you get it from?
Q is also a part of the data of an algebra.
Since you're looking at algebras in the category of chain complexes.
Exactly, yes.
In chain complex Q.
Absolutely right. Yes. So here I wanted also to mention that the homology of the operand of framed little disks is something that's well known, and it's called the BV operand, or operand of BV algebras. BV operand. So, and it is generated by classes by certain special classes. So this is kind of the situation when I let me just draw some pictures here. So this is kind of this represents a zero cycle in the n=0 component of this operator, so the trivial one. This is a zero cycle corresponding to like having two disks cut out which are not moving, and this represents kind of a one cycle in the component of the operator with two disks cut out, where one disk is sort of running around the other disk. And there's another generator, which is kind of most important for us, which corresponds to cutting out one disk and then making a full rotation of this marked point on the disk. So that's also one cycle in this operand, and together using compositions, it generates all the homology, and there are also certain relations. So this is kind of the very important cycle for us. Let's call it a PV cycle, and kind of the integral of C over that cycle is called in field theory sometimes the PV operator. So it's Z evaluated on that cycle. And it is an operator from the space of states for the in circle to the space of states for the out circle of degree -1. And also, well, in conformal field theory, it's usually denoted G0 minus. So that's kind of the name for that operator. So in particular, I can go to cohomology. If I reduce to the Q cohomology of the space of states, then in this reduced picture, this cohomology of the space of states carries the structure of a PV of an algebra over this operand. So it gives a PV algebra. So it has a unit corresponding to this picture, a product corresponding, commutative products corresponding to this picture, a Poisson bracket of degree -1 corresponding to this picture, and a PV operator of degree -1 corresponding to this picture. So I should say that this PV operator is different from the one that appeared in this in minor Konstantin's talks before. So this one, in particular, this one has degree -1, and it's not just a quirk of notations that one had degree +1 and this has degree -1. So a careful observer might notice that the difference between +1 and -1 is 2, which is the dimension of this field theory. So, okay.
Could you explain what H is, the curly H?
Yes. So okay. So this is kind of the so the idea is that I'm putting some kind of state sitting in H on each circle, and I'm reading off the state on the space of states for the outer circle. So that's one way to think about it. The other way to think about it as kind of in the physicsy terms as a OPs or rather multi-OPs. So it's usual OP if I have two disks cut out. And if I have then I should think of having a field here in the center of the disk, a field here in the center of the disk. So I have sort of, and I want to express the product in terms of fields corresponding to the outer disk, which I interpret as field sitting at the center of the disk. So it's an OP. I think Owen was explaining yesterday in maybe much better than I'm trying to do now. But here also you can allow more disks, so that's sort of a multi-OP picture.
So could you explain how we get Poisson bracket from the third picture?
Yes, so Poisson bracket is the evaluation of Z on this cycle.
Yeah, but I don't know what that means.
Right. So this cycle means that one field is is making a full circle around the other. So one can write sort of explicit. I'm thinking like what would help here. So for instance, if you have, I don't know, in topological conformal field theory, two observables, O1 and O2 point observables, then you can perform CMW, then you can do what's called Witten's descent, so produce a one-form observable out of one of those, and integrate over W. So that's another picture of what's going on here. So that's the Poisson bracket between O1 and O2. That's sort of another realization of this picture. I don't know if this helps better.
Maybe just unravel the definition. So right, the C is a differential form. So you compare it to a cycle,
Yeah.
and you get an element in home,
Yeah, exactly.
hence the square to H. Right, and the cycle is given by it's a configuration of disks where one disk moves from the other.
Exactly. Yes.
In this case, configurations of disks.
I see. So if you evaluate on this sort of one-dimensional cycle, then you don't use most of the C form, which is an inhomogeneous form.
I'm only using the one component. Yeah.
Component integrated out, and then, as Konstantin says, you get an element in this home space.
Absolutely.
Okay.
Yeah. Thank you, Vincent. Yes. Thank you. So, all right. So that was all motivation. So I have very little time to talk about what we did, but okay, that's okay. Let me see. So yeah, we want to construct some kind of combinatorial model for this story. So okay, so combinatorial model. So okay, so fixing some kind of a surface, instead of having the space of geometries on the surface, we'd like to think of some kind of CW complex of triangulations of the surface, complex of triangulations. Of the surface, or also let me call it partner complex. So let me say more here. So, well, understanding the details of this object is, well, we don't understand most of the details. We have some desires about what we would like it to be, and we have some sort of partial models. But what we would like to see is that its vertices of psi, correspond to triangulations of the surface. And edges correspond to partner moves. One of the two possible moves, either the flip or the, I erase it, either the flip or the stellar subdivision / stellar aggregation. So then we would like to say that the partition function now would be a non-homogeneous cellular cochain on psi. Instead of being a differential form on some kind of space geom, which was either the moduli space or the space of configurations of disks, now it should be, instead of differential form, it's a cochain. It's a reasonable replacement for differential forms, right? And again, with values in ohms from the in space to the out space. So we would like this picture. Moreover, we would like, well, the main kind of topologicity equation to hold. We would like that the cellular coboundary operator on psi plus q annihilates z. So that's also a reasonable replacement for the equation that we had before. So now deram on the space of geom, which was in examples, it was deram on the moduli space or deram on the configurations of little disks. Now it becomes a cellular coboundary operator on psi. And so reasonable replacement. Again, if I look at the lowest degrees here, I will get that C0, and that's now the zero cochain part, which means that this model evaluated actually on triangulation. So vertices of psi correspond to triangulations. Zero cochain sits in vertices. So that object is Q closed. And next equation tells me that if I consider the cell boundary operator of that, it is Q exact. What does that mean? So that is something that lives on edges, on one cells of psi, and edges correspond to partner moves. So it exactly tells me that when I perform a partner move, then Z changes by Q exact term, and Z1 sort of records the homotopy for that. Okay, so that's kind of the desire, and then we would like to sort of add higher cells. And higher cells, okay, what does one want to add higher cells? Ultimately, to keep the homotopy type of psi in check. So that, yeah, otherwise adding edges but failing to add sort of 2 cells, 3 cells, and so on, you would sort of homotopy type of Xi will explode, and we would ultimately like the homotopy type to be the correct one, to be the same as the homotopy type of the moduli space. Okay. By the way, I should maybe mention that the two models I gave, they are not contradictory to one another, so that the moduli space M equal 0 n plus 1 is homotopy equivalent to the framed little disk operator. So observation. So the models are actually compatible. Now, okay, so first model for this picture is if we forget about Buckner the second Buckner move about the stellar subdivisions and aggregations. So and then it's actually a reasonable model that one can construct here, kind of a flipped model of combinatorial TQFT. So as an input, so now I want to sort of return to the original setting with two-dimensional digraph-Whittle model, but I want to fix an algebraic input. The algebraic input will be, instead of being an associative algebra with a pairing, now it will be a cyclic A infinity algebra. So it will be A infinity algebra with a unary operation M1, which I also called Q, the differential. Then there will be M2, M3, and so on, and the pairing. So this is a cyclic A infinity algebra. So we already know very well what an A infinity algebra is, and this is just an A infinity algebra with a pairing, compatible pairing. What does compatible mean? It means that if I take the operation Mn with n inputs, and then I revert the output using G, so that becomes an operation with n plus 1 inputs and the output in the ground field, let me call it Cn plus 1. So this should be symmetric under cyclic permutations of inputs. Yes, please.
Sorry, question about the previous thing. So psi is enormous. It's like an uncountable number of vertices.
It's huge, yes.
So it's not in any way controllable.
So it's a big question actually. Like how to construct the model for Xi, which has all the properties that we like, but there are sort of partial models which are much more tame, so which are finite. So there are essentially two models that, well, I'll probably be able to talk only about this model, where kind of number of vertices is fixed. Then if you consider triangulations up to homeomorphism, then it will be a finite CW complex. And there's another model where you sort of fix the maximal set of vertices, where you are allowed to remove vertices from your game, but you're not allowed to add new ones. That also results in a finite complex, and there's a model for it coming from so-called secondary polytopes of Gelfand, Kapranov, and Zelinsky. I'll probably not have time to talk about that, but it's a well, you can ask me something. So okay, so now we fix a surface and a collection of vertices. So, and there should be at least one vertex on each boundary. So I'm allowing surfaces with boundary. So the surface and P a collection of vertices. So then, well, we can consider the sort of, let me call it flip complex, the Xi flip of sigma comma P. So P is this set of vertices. So it's a CW complex where the vertices or zero cells are triangulations of sigma with vertices at P. So I don't know, some kind of triangulations. Then it also has 1 cells, 2 cells, and so on, and a K cell, degree K cell, corresponds to a polygonal decomposition or just cell decomposition. We call it polygonal decomposition because I wanted to think of 2 cells as being polygons. Polygonal decomposition, let's call it alpha of sigma also with vertices at P. So the corresponding cell, let me call it E sub alpha, and the dimension of that cell, well, it's a sum over polygons. So for instance, okay, to draw a higher cell, I should draw some cell decomposition where not all 2 cells are triangles. They could be something higher. So it will be a sum over two cells, so sum over polygons. Cells P. So I should, for each polygon, I should take the number of sides minus 3. So actually excess of each polygon above the triangle, and I should add those. So this will be the dimension. Okay, that's the dimension of the cell. So the boundary of a cell is given by all possible ways to subdivide one single polygon by one single diagonal. So boundary corresponds to taking one polygon and subdividing it by some diagonal, for instance, like that. So that corresponds to the boundary of the cell. So combinatorially, those cells, what do they look like? Actually, they look like they're combinatorially equivalent to a product of Starship's associahedra, or a product over polygons. So I take the appropriate Starship's associahedra. So yeah. So for instance, if it's a triangulation with one defect, which is one polygon, that would be a single Starship's associahedron times a collection of points. So okay. Now what is the TCFT then here? Or combinatorial TCFT? Well, how to construct it? So it's what I call a flip theory, or flip model of combinatorial TCFT. So, well, that's a cochain on the flip complex. It's a cochain on the flip complex with coefficients in ohms from H in to H out, and I wanted to construct it explicitly what it is. And the construction is essentially what we saw in the beginning of the discussion today. So, right. So if I have some, so the space of states for a triangulated circle will be just V to the tensor power the number of intervals into which a circle is triangulated, and Z should be a cochain. So I should tell you what's its value on a cell, on any cell of that cell complex. So if I take a cell corresponding to some polygonal decomposition, then it is it's defined by essentially the formula that we had in the beginning today. Well, it's a tensor product over the polygons, the corresponding structure tensor of the A infinity algebra, and these sort of contract along edges using the inverse metric. So it's the same formula as before, but now you don't have just triangles, you have also squares, pentagons, and so on. So squares are decorated essentially by M3, or cyclic version of M3 operation in the infinity algebra, pentagons by M4, and so on. So somehow, maybe I should say that this means that M3 as something associated to the square is a combinatorial replacement for the field G, for the sort of this homotopy for the stress energy tensor. So somehow M3 plays the role of the primitive for the stress energy tensor. So okay, so what should I say here? So well, this construction satisfies one kind of obvious property, that is functoriality. So Z defines a functor from coordisms equipped with polygonal decompositions to vector spaces. That's kind of obvious from the construction. And secondly, and that's a little bit less obvious, but it's a nice observation, that it actually satisfies our topologicity equation, the main equation. It holds here, and well, it holds by virtue of the A infinity relations for the structure constants here, for the structure tensors, that the combinatorics of A infinity relations is the same as the combinatorics or here, the combinatorics of the adjacency of cells in the complex, which is given by subdividing a polygon by a diagonal. So that is to say, you can interpret an A infinity relation, like let's say, as Q of C5, let's say C5 is as something associated with the pentagon, is the sum over 5 ways to put a diagonal inside the pentagon. So that's a way to understand and the infinity relation of one of those infinite relations. So that combinatorics is exactly the same as this combinatorics, which results in this equation. So okay, so let me maybe take 3 more minutes, two more minutes, and I'll be done. So okay, so one thing maybe that I should say is that, well, I was sort of insisting on the BV operator in the world of the framed little disk operator. So one might ask, is there a replacement for a BV operator here? The answer is that yes, there is. So and well, I had some pictures, but it takes some time to set up the machinery. So let me maybe just say in words. So one has combinatorial BV operators. And to find the combinatorial BV operator, you want to find some one cochain in the flip complex of an annulus, or let me draw it as a cylinder, where I take, well, let me take the same amount of points on each boundary and some amount L of bulk points. So I call such one cochain, I call it a BV cycle. Is a BV cycle if the boundary of C is 0, so it is a cycle, and if it sort of squares to a boundary, if the composition square of C with itself, which leaves sort of in a twice longer cylinder, if it is a boundary of some 3 chain. So it turns out that it's a slightly non-trivial problem, or somewhat non-trivial problem, to find examples of such BV cycles. So the most naive thing that you would draw with like 1 point on each boundary and 0 points inside, there's kind of a naive candidate for which it doesn't work, surprisingly, because somehow, well, this lives in the flip complex with more bulk points, and that sort of screws up the homotopy type of the flip complex. So the square will actually give a non-trivial element in the second homology of the flip complex for this naive representative. But there are non-naive representatives which, with Justin and Donald, we have found. So they're actually non-trivial BV cycles. Well, to be honest, we found them, but we couldn't rectify the sign, so they leave modulo 2, and we didn't find those that work with signs. But okay. Now, then, if I evaluate my theory on that cycle, that is some operator from the space of states for a circle triangulated into k intervals to itself. And well, what this equation means is that, well, first of all, this operator is Q closed, and secondly, its square is Q exact. So, for instance, in Q cohomology, it projects to Q cohomology, and there the projection would square to 0. So it is a reasonable replacement for BV operators. This is the combinatorial BV operator, or combinatorial operator G naught minus. So okay, let me see. So then the project is to somehow put the second factor move in the game, and kind of one model where it is possible is based on Gelfand, Kapranov, Slivinsky secondary polytopes. They would replace the flip complex here, but they can exist only on a single polygon, and sort of trying to extend that construction to general surfaces is a dream. So the dream is actually to have the correct Partner complex, which sort of has kind of edges corresponding to both Partner moves in it, and has the correct homotopy type of the framed little disk operate, or in genus 0, or in general genus, the homotopy type of the modular space of modular space of complex structures. So that would be kind of a proper combinatorial TQFT. I wanted to finish just, can I maybe show one picture? Is it possible, just as a last slide? So just kind of a dictionary between the combinatorial and the, yep, there it is. it is a dictionary between the combinatorial and the continuum theory, sort of summarizing what I said and some things that I didn't have time to say. So maybe the interesting thing is that the square is a homotopy for the stress energy tensor. I guess that's maybe one thing to remember here. Let me finish here. Thank you.
Questions for Pavel?
I have a lot of questions, but perhaps I shouldn't reveal the full depths of my ignorance. But one of the first things I'm wondering is, so you said something about how the re-triangulation is related to the stress energy tensor. I don't really understand that. Can you maybe give some kind of physical?
Okay, this is kind of a metaphor. That a triangulation is like a metric. But what is not a metaphor, what is sort of a construction in physics is what is a stress energy tensor? So a stress energy tensor is the reaction of the theory, either classical or quantum theory, it exists in both worlds, to it's essentially it's a variational derivative with respect to a local variation of metric.
Yeah.
So you essentially you cut out a tiny disk out of your space-time manifold and you change the metric there and you just look how does the answer change, and the answer could be the action, then this variational derivative is called the stress energy tensor in the classical theory, or you could do it with a partition function, and partition function could depends on the metric. Let's say you change the metric a little bit, then you would say that it's a correlator or expectation value of the stress energy tensor in the quantum world. So, and here what I was telling is a metaphor where kind of a metaphor for a metric is a triangulation, and somehow the metaphor and okay on a surface metrics. Okay, a metric induces a conformal structure, right? And then I can sort of move metrics kind of by changing the conformal structure, or I can change the metric by not changing the conformal structure, which is called the Weyl transformation. So in these two types of deformations of metric, they are modeled here by Wagner flip, which we think of as changing the conformal structure, and Weyl transformations are modeled by the second Wagner model. So you should think that you are sort of adding more vertices, so you're making more triangulation, your triangulation more dense locally. So that's like doing a Weyl transformation, which increases the metric by Weyl factor. That's sort of a metaphor. Yes, please.
So there is another way we can express failure of associativity in chains by like the Stirrup operations. I was wondering if there is a connection.
I don't know. So maybe you explain me what you mean, but sort of maybe later. Yeah. I'm afraid of characteristic too. So yeah, I kind of think about standard operations, but maybe you tell me.
Like this cup one.
Oh, you mean not standard squares. Well, anyway, so I cannot say anything meaningful now. So maybe let's discuss separately.
So Kevin also worked on TCFTs, but in a very different way. And one of the things he showed was that if you had a functor in that setting, a TCFT in that setting, you got the solution to the master equation by taking the Sens-Wiebach fundamental class, which is like a solution on the cochains of the moduli space, Riemann surfaces, and you get it in this BB algebra you make from the closed Hilbert space. So sim of the cyclic homology of V. And I'm just wondering, is this like, do you expect there to be, like you just talked about the genus zero part, but do you expect some sort of like bigger?
So I think, okay, I sort of, I don't remember well Kevin's paper, but if I remember correctly, he was going kind of in the Gromov-Witten direction. And that means that he was working with a okay, there are different moduli spaces. There's the compactified and the non-compactified one. So this is the non-compactified moduli space with this extra sort of formal chart at a puncture. That means that there is this cycle corresponding to making a rotation around the puncture, which is the PV cycle. So if you instead consider the compactification of the Ling-Mumford compactification, then there are other cycles which correspond to kind of Gromov-Witten invariance. That's kind of a different story. And I think that Kevin was kind of working with the compactified moduli space.
He works with the uncompactified one. He relates it to the compactified one. There's a map, right? So you get a map on. cochains the other way.
So I think that's sort of, yeah, so the BV operator doesn't have any sort of trace in this compactified modular space. Rather, it's kind of essentially having a non-trivial BV operator in a TCFT is an abstraction for correlators to extend to the compactified modular space.
Right.
Other questions? Okay, well, if not, then let's thank Pavel. Have lunch available around the globe.